reaching altitudes of a few hundred kilometers. Why people are interested in Europa in the first place is because under its surface of frozen ice, there's probably an ocean of liquid water where life could be possible. And this talk, I'll be talking about how we know that Europa has this ocean and how we could use these plumes to get an idea of what's inside the ocean. And along the way, I want to give a bit of an inside view how scientists reach their conclusions, how it happens in practice. So that's a bit general overview of the talk. A little bit about my own background. So I was already introduced, but just to summarize, my background is space engineering. So I started studying the technological side of space missions. I ended up doing space science. I worked a bit at the Swedish Institute of Space Physics, and now I almost finished my PhD at the Max Planck Institute for Solar System Research in Germany. And from next year on, I'll be working at the European Space Agency. And the main thing that I've been interested in is Jupiter's moon Europa, which is by no coincidence the topic of today's talk. Let's start a bit in general. Why do we think that there's life on Europa? That's the first question I would like to address. So, who of you has seen Europa with their own eyes? Just raise hands. With a telescope, I count that as your own eyes. So not everybody, I'm surprised. So if you ever get the chance of taking your binoculars or telescope and look at Jupiter, you'll see pretty easily that there are 4 dots next to Jupiter, and these are the 4 biggest moons of Jupiter, the Galilean moons, and one of them is Europa, so you can easily see Europa yourself. But
Which one of those? Which one of those?
Which one of these is Europa? I was just asking myself the same question. I actually don't know for sure which one of these is Europa. But if you look, yes, closer at Europa, you'll see something like this. So this is Europa, and the surface, it's white because it's made of water ice, and there are a lot of these special features, lots of things that are effectively cracks. Why there are these cracks, I'll talk about later. Alright, this is a family portrait, so we have 2 sides, Jupiter, and its 4 biggest moons. We have Io, Europa, Ganymede, and Callisto. Of course, the distance is not to scale, but the size is. More comparison on the next slide. So to get an idea how that compares to Earth, so Europa is a bit smaller than Earth's moon. And as I already mentioned in the beginning, under this icy surface of Europa, there's an ocean of liquid water. I'll tell you later why we think that there is an ocean. And whenever there's somewhere liquid water in the solar system, scientists get excited and they think, oh, maybe there's life possible there. I'll get to that next. The ocean of Europa is pretty thick. So estimates go that the ice layer is from a few kilometers, like 2 to 10 or 20 kilometers thick. And the ice layer, the water layer, could be actually up to 100 kilometers thick. So that's a lot thicker than the oceans on Earth, and as a consequence of that, the total volume of water on Europa is probably bigger than the total volume of water on the surface of the Earth. The Earth's surface oceans are at most 10 kilometers thick, but on average not that much less. So that's why Europa, which is 100 kilometers thick ocean, has a lot more volume of water. By the way, if you have any questions, just feel free to ask them during the talk. You don't have to wait till the end. I don't know what's your content, so just to clarify that. So, ocean, next the light. So I like showing this picture. This is some kind of artist impression of what life could be like in the ocean of Europa. I like showing it because it gets some things wrong. It's very right about some other things, and maybe a little bit optimistic about some things. I like monsters, but I'm afraid that the artist was a little bit too optimistic about what life could look like in Europa's ocean. Probably we shouldn't expect big sea monsters to be swimming around in the ocean. We might have to be satisfied with just simple life forms like bacteria, if there is life in the ocean. It might be restricted to simple forms of life. Artist is a bit optimistic about the types of life that we could have there. And that brings me to the next question. I'll get back to the painting later about things that are right and wrong. So, why do we think there's life in Europa's ocean? To answer that, maybe it's important to ask the question first more in general, what's needed for life? That's a very complicated question that takes a lot of time to answer, but looking at life on Earth, there are at least 4 very basic requirements that can be formulated to have life somewhere. On Earth, all life requires liquid water. It requires some basic chemical building blocks, sulfur, phosphor, oxygen, nitrogen, carbon, and hydrogen. It requires time, so water needs to be liquid for a very long period of time to give life a chance to originate. And we need some kind of energy to make the life live. So let's get back to the painting. So to peek ahead, yes. So in case of Europa, we do know that liquid water has been there probably during the entire existence of Europa. And Europa was formed during the formation of the solar system, which is about 4 to 5 billion years ago. So we definitely have liquid water in Europa, and we've had it for a period that's probably long enough for life to originate. At least it did during 5 million years on Earth. We know that those basic building blocks for life are probably there. We have either measured them, or it's very likely that they occur in Europa. The last important thing is energy. Is there a source of energy for life on Europa? So now I can get back to the painting. So there's one thing related to energy in this picture that might be a bit wrong. Does anybody have a guess?
Bubbles?
The bubbles are not what I'm looking for.
It's too light, too bright.
It's too bright, yes, it's exactly what I was looking for. This ocean of Europa is covered by an ice layer, and the ice layer is, as I said, at least a few kilometers to maybe 20 kilometers thick. That's unlikely that much light is going to get through there. So Europa's ocean is not going to be light at all, it's going to be very dark. And on Earth, the light of the sun is the main source for energy for life. All life depends directly or indirectly on the sun. We eat plants that need the sun to grow, or we eat animals that eat plants that need the sun to grow. So this kind of life that requires energy from the sun is unlikely what's going to be happening on Europa. But there is a potential solution, and those are bubbles that I think are the thing that might be correct about this painting. We have something like that on the bottom of the ocean, and we think the same might be occurring at Europa as well. So back in the 70s, people went to the bottom of the ocean with this submarine. They found the Titanic with this one, but they also found something else, and that is this phenomenon. It's called black smokers. These are hydrothermal vents on the bottom of the ocean. Very hot, boiling water is seeping through cracks in the ocean. And this water is very rich in minerals, and that explains why it's so dark. It's plumes of dark water boiling out from the bottom of the ocean. And we assume that the same might be happening on the bottom of the ocean of Europa. So I forgot to mention something very important about these sources of hot water. What makes them so interesting is that they are surrounded by life. Life has found ways to use energy to create energy using the minerals in these hot water sources. There are bacteria that have evolved to use substances in these hot water sources to provide energy from the cells, and various other life forms have evolved that eat these bacteria and thus indirectly live off minerals in these hot water sources. The main point is that they don't need solar energy to live.
Is that coral?
These are not corals. These are tube worms.
Worms.
And the red things they use to filter the bacteria out of the water, and it's these bacteria that get energy out of the black smokers. And so it is assumed that these kind of black smokers could be occurring on the bottom of the ocean of Europa as well. Thus, there's a potential source of energy in the ocean of Europa. So even though there is not much light, life could still have originated or could exist through means of these hot water sources. So, to summarize, all the requirements for life on Earth-like life are met in Europa. We know that there's liquid water, we know that the chemical building blocks are there, we know that the liquid water has been there for enough time to form life, and we know that there is a potential energy source for life. This is why scientists assume that life could potentially have evolved in the ocean of Europa. And that's why Europa receives a lot of attention in the planetary science community. So I've been assuming that we know that there is an ocean as a given thing up to now. I'd like to explain now why it is thought that this ocean is there. Because obviously nobody has ever seen this ocean with their own eyes. It's always covered by this ice layer, and we cannot get through the ice layer. So how do we even know that there is this ocean of liquid water? I'd like to explain now how this scientists have come to this conclusion. So the first reason why we think that there could be an ocean has to do with Europa's surface. This one on the left is Europa, of course, and on the right, if you remember from the family portrait, this is another moon of Jupiter, it's Callisto. And I need your help here. What is the main big difference if you compare the two? Any guesses? Impact craters, you already know. So Callisto has a lot more impact craters than Europa, which is in a way surprising. They're both orbiting Jupiter, so you'd expect that throughout their life, the amount of comets and asteroids impacting on them and other parts of dust should be about the same, right? But Callisto somehow has a lot more craters, while on Europa, we actually, except maybe this big one, we don't really see any craters. Especially if we zoom in, that becomes very clear. So this is the surface of Callisto. We see craters, and in every crater we see another crater, and if you look closely at that crater, you see there's another crater, and that crater, and that crater, and so on. It's like a fractal. Craters everywhere. But if you look at Europa, we see a lot of other stuff, but craters, not much.
So why would one have craters and not the other?
So probably Europa has craters too. Exactly the same number of craters, or at least the same number of average craters per surface, but Europa must have something that is constantly renewing the surface. So this leads us to think that there must be something under the surface, like liquid water or some ductile ice that's replacing the surface that's damaged by craters. Actually, I was misleading you a little bit. There is a very big crater in this picture that will help me explain what I've just tried to explain to you already. So this is a crater. It doesn't look like this at all. You just see a bunch of rings. What likely happened here is that something impacted Europa's surface, but the hole left by the impactor was filled up by fresh material, at least in the middle, and then we just see some rings caused by the impact. So Europa's surface looks like it's trying to erase all the impacts that happened. So that means that under the surface there must be something that can do this, that must be liquid slushy-like ice. Let me get to that in a bit. There are more signs that Europa's surface is something moving, something constantly changing. So this is a type of surface terrain that we've only observed on Europa. It's called chaos terrain because it's pretty chaotic. It looks like pieces of a puzzle that are somehow mixed up. The first people that saw this might have considered that it's a bit like ice shelves on Earth. Ice shelves that broke up and started drifting with respect to each other. And they realized that this is actually something very similar. So the first people who analyzed these pictures printed them out on paper, cut out the pieces, and put them back together. And if you do that, then you'll get back the original surface. So what happened here is that we had the surface of ice with a lot of cracks, and somehow it became mobile, and the pieces started drifting with respect to each other. And that means that under the surface of solid ice, there must be something movable, like liquid water or something slushy. So what we learned from the surface of Europa is that under it, there should at least be something liquid or some of the slushy material. It's frozen water, but movable. We can't tell for sure by looking at the surface if it's liquid or movable. Yeah.
So there would also have to be a source of energy to move the water around?
That's a good point. The reason why it's moving, I'll get back to that later. But yeah, there's a source of energy needed. So that was the first reason why we think that there might be some slushy or liquid layer. The second reason has to do with gravity, Newton, and this thing, the Galileo spacecraft. Actually, most of the stuff that we know about Europa is all coming from this space mission that flew by Europa 10 times between 1995 and 2003. It's an American mission. And one of the things they did with this space mission was try to get an idea of the gravity of Europa. So to explain it with a very basic comic, so let's say if we're flying with a spaceship through empty space with nothing in our vicinity, then the path of the spacecraft would be just straight. But as soon as we get close to something massive like Europa, the gravity of Europa will bend the trajectory of our spacecraft. That's what gravity does. But the way that the trajectory is bent but depends on the interior composition of the object. So if we have an object where all the heavy stuff is in the center and it's not homogeneously spread like here, then since the heavy stuff is a bit further away from our spacecraft than the lighter stuff, then in this situation where it's just homogeneous, then because the heavy stuff is further away, the effect of the gravity force is a bit weaker, so it will affect the trajectory in a different way. This is a bit of an oversimplification, but the main point is that depending on what kind of layers you have on the inside of your object, the bending of the trajectory will be different. And this is something they were able to measure, not with a lot of precision, but enough precision to tell that on the outside of Europa, there should be a layer of which density is consistent with that of water or ice. So that's a second symbol, signature that tells us that under Europa's surface there should either be liquid water or the slushy material.
So can you just go back to that for a minute? So the water, the red would be the core, and the water would be the blue, is that right? That's the deal.
I tried to come up with an example, so this is not necessarily Europa. I just meant to say that if you put all the heavy stuff in the middle rather than have it evenly spread, once it's in the middle, it's further away from the spacecraft and it's less of an effect on the trajectory, so the bending will be different.
So is it assumed that within in the center, the core of it is some sort of rocky material?
Yeah,
it's heavier than the water.
Yes, exactly.
Okay.
Europa has a rocky core
Right.
and this lighter layer underneath. And they've been able
And
to.
they therefore the gravity would be strong. It would move, an object would not be as close. Okay.
Yeah.
I got it.
That's a bit of an oversimplification,
Sure,
but
sure. It's probably very slight. Really.
yeah. But they've managed to measure difference and correlate it to the layers inside. So, okay, there are a lot of reasons why you think there's a liquid water ocean. If you bear with me, I have one more, which is related to magnetic fields. So this is a simple experiment. Maybe people have done that at school or at home. If you take a magnet and you'll put isofilings around it, you'll start seeing the field lines of the magnet's invisible magnetic field. What does this have to do with Europa? Europa is exposed to a very strong magnet, and that magnet is Jupiter. Jupiter has an internal magnetic field that's very strong. If we would visualize Jupiter's magnetic field on the night sky, it would be the biggest object that we could see. So we see Jupiter as a star, but what this schematic illustrates is the extent of the influence, is the region of influence of Jupiter's magnetic field. And this magnetosphere is a technical term, and this region where Jupiter's magnetic field extends is so big that it would be the biggest object in the sky. Why do I show this? I just want to make the point that Jupiter has a very strong magnetic field, and that Europa is exposed to this strong magnetic field. And what Jupiter's magnetic field does to Europa is a bit like an MRI scanner. So an MRI scanner uses strong magnetic fields that are exposed to the human body, and the body gets a reaction on this that is measured, and that reaction is used to get an idea of the internal structure of the human head, for example. And in this case, we have our very strong magnet, Jupiter, and our patient is Europa. Europa has a certain reaction to the magnetic field of Jupiter that has been measured, and that has been used to get an idea of what Europa's like on the inside. So, to explain this a little bit in more detail, so Jupiter has a magnetic field. This is the axis of magnetic field, and these lines indicate the field lines of a magnet. And Jupiter's magnetic field is actually tilted with respect to its rotation axis, and thus with Europa. So Europa is rotating in this plane around Jupiter, but the magnetic field is tilted with respect to this field, with this plane in which Europa is rotating around Jupiter. What does that mean? That means that from the point of view from Europa, the magnetic field is actually constantly changing. That's the main thing I want to get out of the schematic. And there's this very simple analogy. If you have something conductive, this wire for example, and you move a magnet with respect to the conductive wire, then an electric current will be created. That's Faraday's law of induction. You might have heard about it before. And in this case, the moving magnet is this magnetic field of Jupiter that's moving with respect to Europa. And Europa has a conductive layer inside, because we see that while Europa is moving with respect to this varying magnetic field, Europa starts creating its own magnetic field. So Jupiter's field is moving with respect to Europa, and at the same time, we see that Europa gets its own magnetic field. What's happening is Europa must have some conductive layer on the inside, and while it's moving with respect to the magnetic field, electric currents are created, and it works the other way around as well. Once you have electric currents, a new magnetic field is created, and that's what has been measured. So complicated. We have Jupiter and we have Europa moving with respect to the magnetic field, or actually the other way around. That creates electric currents inside of Europa, inside of a conductive layer, and these currents on their own start generating magnetic field again. And that magnetic field has been measured. And what these measurements tell us is that there has to be this conductive layer, and it has to be at the outside of Europa. We already knew that on the outside of Europa we probably have a layer of ice or slushy material. But now, from these magnetic field measurements, we also know that this layer has to be conductive. Otherwise, we wouldn't measure that it creates a new magnetic field as a consequence of Jupiter's magnetic field moving. And let's put all this together. So we've looked at the gravity, and by looking at how the spacecraft moved with respect to Europa, we know that there has to be a liquid or slushy layer on the outside. By looking at the lack of craters and the moving pieces of the surface, we know that there has to be a liquid or a slushy layer. If we look at what Jupiter's magnetic field does to Europa, then we know that there has to be a conductive layer. That this layer on the outside, which is either water or slushy, has to be conductive as well. And we can measure how conductive it has to be. And what happens to be, it doesn't have the same conductivity as slushy, because the conductivity of frozen water is different than that of water. So the only option that remains is liquid water. So it's a bit of a messy story, but the main point is that by combining all these different types of measurements, they were able to figure out that there has to be this liquid water ocean. If it was a bit confusing, the point that I want to make is space science is not like Star Trek or whatever. In science fiction movies, when they arrive at a new object, somebody presses a few buttons, and in 1 minute they figure out everything that there is to know about the object. It's really never like that. We always have a limited number of measurements and instruments that can only measure a very limited number of things. We always have to patch together these different things of information that at first sight don't have anything to do with each other. It's a bit like, space science is a bit like a puzzle where you have lost the picture of the box and half of the pieces. And you're left with half of these pieces and you try to put them back together to get an idea of what was on the picture of the box. In this case, the picture of the box is the liquid ocean, and the pieces are the lack of craters, the magnetic field, and the gravity. If you put them together, then you know, it must be an ocean.
What about, since the magnetic field is caused by Jupiter, wouldn't, and Faraday's law with a magnet, that with a coil, that induces voltage, and voltage causes lightning. Because water is a conductor of lightning.
Yes. Let's say on this slide. So you're right. So the Europa's moving, or the magnetic field seems to be moving with respect to Europa, which creates currents.
Yeah.
And they're already there. There must be some kind of electric current in Europa's ocean, and it's this current that creates the magnetic field that we measure. You're asking if there's like a short circuit between Europa and Jupiter, like to get these currents back. That's a very interesting question.
Because magnetic field.
That's interesting.
Yeah, I'm sure these have not been measured, so
Yes.
that leads me to think that there's a reason why they shouldn't be there. But
As I said, you've got storm clouds over the ocean, on Earth, and lightning.
as David says, it's probably not strong enough to have these currents back to Jupiter.
Yes.
One thing I was going to ask, salt water conducts more than fresh water, so can you tell whether the water is actually fresh water or salt water?
Yes,
from these
right,
measurements?
that's a good point. So it's salty water. The conductivity corresponds to salty water. I forgot to mention that. Because otherwise it would not work like this. So it must be salty water. Yeah.
Does Europa have an atmosphere of any sort?
Europa has a very thin atmosphere. There's a thin layer of gas around it.
What kind of gas? Methane?
It's there. gas is evaporating water ice, and through this chemical process, this leads to oxygen. Most of this gas layer is oxygen, O2. This is not the end of the presentation yet. I have more if you're still interested. So, up to now I've told you why we think there's an ocean and that life could be possible there. And now, as somebody already touched upon in a question, why is there a liquid ocean? So, there's this famous picture of the habitable zone. So, this is the distance with respect to a star, in our case the sun. And depending on what kind of star you have, there is always a region in which water will be liquid. If you get closer to your star, then that distance and your water will just evaporate. If you're further away, it freezes and you won't have any liquid water. This is Jupiter. Europa is definitely outside of this habitable zone, outside of this region where you should have any liquid water. So that might lead you to ask, why is that water liquid in the first place? Where's the energy coming from that keeps the water liquid? That's a good question. It has to do with gravity and Europa's orbit around Jupiter. So Europa is orbiting Jupiter in an orbit that's more or less circular, but not perfectly. It's a little bit elliptic. I've overdone it in this picture. Europa's orbit around Jupiter is slightly elliptic. That means at some points during its orbit, it will be further away from Jupiter than during other parts. And what Jupiter's gravity does to Europa is that it elongates the moon, it stretches the moon a bit. When Europa is closer to Jupiter, the effect of Jupiter's gravity in Europa is a bit bigger, and it's elongated a bit more than when it's further away from Jupiter, and it's elongated a bit less. So while Europa is rotating about Jupiter, it's going from more elongated to less. And this video illustrates what that looks like from the point of view of Europa. So while Europa is rotating around Jupiter, you see its shape changing from more elongated and to less elongated. The same the whole time. And now I want to do a small experiment that my professor at university used to do with us as well, to make us understand what this has to do with Europa's liquid ocean. Don't give it away if you've already figured out the answer. Or if you know it. So this experiment requires a paper clip. If you'd like to participate, take one. And if you want me as well, so help me distribute it. Maybe I'll take half of the box to make it go faster. Please. I'm going to give a few at the beginning of each row, and then you'll hand it through. Could you help the gentleman as well? 1, 2, 3, 4. Yep. If you could give me your thoughts. Does anyone? Nice. So I'll just give you some random ones. Oh, you have one already? Oh, yeah, sorry. I already went through this reply. So I have 2 more, in case anyone's missing any. You guys all have one? Here? Who doesn't have one yet? Here? Everybody got one? Yeah. Okay. Oh. Yeah.
Do you guys have extras?
So, I'm assuming everybody has one by now. Do we have extras? So, paper clips in New Zealand are slightly different than those in Europe. I discovered right now. But the idea is that you take both legs of the paper clip and you take them apart a little bit like this so that you can hold each leg with 2 fingers basically. So you have to imagine that we have a solid material here and we're going to apply friction to the solid material just as is happening to our solid Europa. So if you take your paper clip and you move the legs up and down a few times, you'll create friction. Be careful or you'll break it. And then if you put it on your lip and you did it well, unlike me, then you'll feel something has happened to the muscles. I'm going to try it again. So you move the legs up and down several times quickly, and then touch your lip. Did you see what I was trying to do? If you didn't, I'll come over and I'll show you from close by. Just let me know. So basically it's like this. Like that. Okay. So, become a bit closer. Yeah, I think some people didn't see it, so I'll demonstrate it one more time here. I'm sorry if it wasn't very clear from the first time. So, you open the paper clip with the legs like this. Please tell me if you can see it. Okay, and then you move the legs with respect to each other several times quickly, like this. And then you feel it. Yes, yeah. Like this? I do it like this. Oh, like this? Yeah. Like this? Yeah, like this. No. Right. I think this works better in a real Europa than here. What was supposed to happen if it went well is that once you start moving the legs to each other, the joint that is part that is moving is receiving friction from us, and the consequence of that is heating up. When you move a solid, not just by moving two solids with respect to each other, but when you move one solid on its own, you create friction inside, and that's basically the same. That's what's happening in Europa. We have this interior of solid material that's receiving friction while we're in this orbit around Jupiter, while its shape is changing.
Expansion and contraction.
Sorry?
Expansion.
Exactly. It's expanding and it's contracting in this orbit around Jupiter, and it creates friction, and that creates heat inside of Europa's interior. It keeps it warm, it keeps the ocean liquid. That's why the ocean is liquid in the first place. Sorry? It's salty, yeah. So, I want to say one more thing about this. So this concept of this habitable zone, that water can only be liquid based on the surface temperature of the planets is a bit an incomplete concept. Often when you hear news about a new planet being discovered around another star, they'll say, oh yeah, it's in the habitable zone, where water could be liquid on the surface because of the heat of the star. That's a bit of a limited concept, because from Europa we know that even far outside the habitable zone you can have liquid water because of this gravity interaction that I just tried to explain to you. So every time you'll hear somebody talk about the habitable zone, please don't forget about Europa. There are other ways it could have liquid water far outside of the habitable zone. And let me now get to the water volcanoes that I mentioned at the beginning. So some observations have been made, a bit more recent, since 2012, that sometimes from Europa's surface there are these eruptions of water vapor about 100, 200 kilometers high coming from the surface. And you can think of this a bit like a geyser. We don't know what's happening under the surface. And in the case of Europa, we don't know the phenomenon that creates the vapor is the same, but the part above, just think of that as being somewhat similar. We get an idea what it's about. So in Europa, we do have these big geysers or water volcanoes, as I like to call them, erupting. And the interesting thing is that, well, this liquid water has to be coming from somewhere. It has to be coming from the ocean, the only part that we know is liquid. So if you could fly through one of those water plumes and take samples, then you could get an idea of what's inside this ocean without even having to land and drill through the surface. Landing on the Europa surface and going through the ice is something that's maybe technically possible, but way too expensive. That won't happen in the next 50 years or more. So flying through one of these eruptions and taking samples could be a more cost-efficient way of getting to know what's inside of Europa's ocean and try to figure out if it really is habitable, as we think. It might be interesting to take a look at why we think that these water volcanoes are there. I didn't show you any pictures yet of these water volcanoes, so you might be getting a little bit suspicious. But there are still good reasons to believe that they're there. We know that because of the Hubble Space Telescope. We don't know it from any probes that were there. I'll show you some pictures of the water volcanoes. There's a problem with resolution, so we'll not be taking a look at the full resolution Mona Lisa, but a very low resolution Mona Lisa. So these are the observations that were made to show that the water volcanoes are real. And you might be thinking, okay, where is that water volcano? Is it there? Is it there? No, it's really here. What is this? What are these observations? So this has a lot to do with aurora that you have in the north and south pole of the Earth. Aurora, auroral light, northern lights, southern lights, and they're created when charged particles originally coming from the sun hit the atmosphere of the Earth. They give energy to the atmospheric particles that release this energy over time, and that creates light. And that is actually what's happening here. It's not those particles coming from the sun, but it's particles moving around in the electromagnetic field, hit the gases that surround Europa, and these gases start glowing. And usually, and these observations in Hubble are observations of that glow around Europa. We can't see it in visible light because it's too weak, but in ultraviolet light we can see Europa glow a little bit. And this is an observation of that made by Hubble. And Hubble has seen that both hydrogen and oxygen around Europa is glowing a bit, or well, oxygen is glowing around Europa. And during this particular observation, they noticed that there was an extra glow in hydrogen at the same place as oxygen. So we have something that's made of oxygen and hydrogen that seems to be glowing. And well, what is made of oxygen, hydrogen, water. So the researchers that made this observation realized that there must be a cloud of water here that's glowing because the particles from Jupiter's magnetic field or moving in Jupiter's magnetic field are hitting the water and making it glow a little bit in ultraviolet
So
light.
they're not actually seen, because you had a slide a few.
There was an artist impression.
Okay.
So the only observations that we have of these water volcanoes, these water plumes, are this. And this is, to get back to my scientific puzzle, so we lost the cover of the box, the nice picture of the plume, we don't have it. We also lost most of the puzzle pieces, but from what we can find, these emissions of hydrogen, emissions of oxygen, they tell us that there must be water. There's no other place that water could be coming from than from inside Europa. So if you put these puzzle pieces together, we know that there has to be liquid water coming out of Europa.
What your water, you said that Jupiter's forces are making Europa change its shape.
Yes.
So if you think about Earth and its plates and earthquakes and things move,
Yeah.
I wonder if that could be fishes or something that are being created that let the water escape.
Yeah, that's what people thought, because at the first time when they saw it, this particular observation happened at a point where Europa was, with respect to Jupiter, at a place where you'd expect these cooling forces that could open the cracks to be maximum. So the first time that they observed it, I thought, oh yeah, that's just because Jupiter is pulling apart the cracks in the surface and letting stuff come out. But they've also seen it at moments when it's not at that position. So it might still have something to do with that, but it's not as simple. At first they thought it's just happening when the cracks are opening, but it seems to be more complicated than that. But the gravity forces will still likely be the will be.
I mean, the moves of Earth, you know, changes tides and
Yeah.
things like that. So
Yeah.
there must be some sort of influence with that one.
Yeah. There's still to be expected a factor of influence on when the eruptions happen, but we don't know exactly how this relation works. Yes. So to get to the final part, so what we want to do is fly through one of those water volcanoes and take samples to figure out what is in Europa's ocean. And we'll get a few opportunities to do that in the future. One thing is a new mission called JUICE, Jupiter Icy Moon Explorer, the worst acronym ever. As you can see, the letter M is not even in there. So that's a new mission of the European Space Agency. It's going to look like this. It's currently being built. It will launch in 2022. It will study Jupiter and its moons, mostly Ganymede, but it will also fly by Europa a few times. So this might be the first mission that will get a chance to actually fly through one of those water volcanoes and give us some more information about what's inside of Europa. So, well, we have JUICE, and the question is, when it flies by Europa, will it actually be able to detect those particles, or are enough particles getting out to be able to detect them with JUICE? That's something that I've been working on. So this JUICE mission has several instruments. One of them is called Particle Environment Package. It's a package made out of 6 particle detectors. What these detectors do is, well, detect particles. They count how many particles are coming in from every part of the sky that it's looking at. The instrument measures how much particles are flying around the spacecraft, how many are coming in from every direction, what mass they have, what energy they have, and through the mass you can get the chemical composition and know what it's made of, and you figure out if there's something interesting in terms of life in the water. So with these particle detectors, we can actually detect the water volcano, or we could detect those particles coming from the water volcano. The question is, do enough of those particles reach the spacecraft to be able to make a detection? And that's something that I've been trying to figure out. So what happens with those particles? Once they get out of the crack on the surface of Europa, where do they go to? How do they propagate to space? Most of them will follow ballistic trajectories, much like a cannon. They'll initial velocity, they'll start flying, and at some point they'll fall back to the surface again. That's what happened to most of the particles. Getting back to that strange magnetic field of Jupiter, some of the other particles, they will become electrically charged because they will interact with stuff that's already flying around in Jupiter's magnetic field. And what happens to those particles is called drifting. Think of it a bit like this, but not quite the same. So we have Europa here, and the blue line is a drifting particle. So this drifting particle will make a trajectory like this through space, which is something very unintuitive, but that has to do with electric and magnetic fields. And these kind of particles, they will come out of the blue, react with particles from the magnetic field, and then they will start making these strange trajectories to space away from Europa. They won't fall back again, which is something very interesting. And so what I did is I made computer simulations. I simulated tens of millions of those particles, both the normal ones and the special ones that are drifting, and calculated if enough of them would be able to reach the spacecraft. And well, it seems to be that we're lucky, even though we're not getting any closer than 400 kilometers to Europa. Enough of them should still be able to reach the spacecraft, and all the normal particles that are just falling back, but also the drifting ones should be able to reach the spacecraft. So that's good news. That's good news for when we reach Europa. We'll be able, if we're lucky, if we catch one of those water volcanoes and we fly through one of them, we might actually get an idea of what's inside Europa's ocean. We have to be patient. We have to wait till 2030 when this mission will arrive. Around that time, it might actually get pretty busy around Europa. The Americans are also building a dedicated Europa mission, the Europa Clipper mission, which might arrive around the same time. These two are approved, so we'll definitely be busy in 2030. And maybe there will even be a lander. NASA is currently investigating the lander to send to Europa. This is still under evaluation. But the other two are approved, they're being built, they'll go there. So I'm counting down to 2030. I hope you are too. And then we, or maybe me, or some people in the audience, might be the lucky ones trying to figure out what really is in Europa's ocean.
We'll be lucky to even be alive by then.
You have to wait till the end to get your PhD.
Sorry?
You have to wait until the end for your
Luckily not. So, and with that prospect in mind, I'd like to end my presentation and take any of your questions.
What's the surface temperature of Europe?
Like 150 Kelvin, so very cold. So yeah, it's minus more than minus 150 or something.
Do they expect that this spacecraft will actually be able to optically detect these ice volcanoes so you can maybe adjust the orbit, or is it just going to be a matter of chance that you do a flyby at a low altitude and hope for the best that you might pass by?
They'll be looking at Europa before they make the actual flyby, and there are some instruments on there that might be able to see the plumes from a large distance. So they might not be able to change the orbit again, but they'll have other opportunities to figure out if the plumes are at least there and how often they happen. But if you really want to get the best kind of idea what's in the ocean, you have to take direct samples. And that's not something you get from distance.
On the image, it shows kind of orangey coloured cracks. Is that just a photo, or is it?
No, they're really like that. So the white is just water ice, and these things that appear like cracks are indeed cracks. Why are they brown? So sometimes water has to be seeping through those cracks. As I said, the water is probably salty, and under the influence of space radiation, this salt over a long period of time starts to become kind of orangey browny. So that's what we are seeing here.
So the position of the geysers changes the ice plates move?
Um,
Or is that something that happens in a visual?
but it's probably the other way around. It's the moving of the plates that determines where geysers are.
So if you are planning to do a flyby in 2030, how will you know where they are?
Yeah, we don't even know precisely where they're coming from. Like this Hubble observation that I showed you, the resolution is so poor that you can't even tell, like, oh, it's coming from that crack or it's coming from this type of surface area. We can't tell, and people have been looking at pictures from Galileo that were taken close by to see if they can see next to cracks any signatures of eruptions, but we just have too few high-resolution images of the surface to be.
So is Juno going to provide any information?
So Juno is currently orbiting Jupiter. It was designed not to come near any of the moons, so it's not in a good position to study the moons. I'm sure they'll be looking at Europa or the other moons to try to see if they can find anything, but the instruments were not designed to make such images, so the resolution will be poor, which doesn't mean that they won't be able to see anything, but so far, nothing from Europa yet.
How different is the composition of Europa to the other Galilean moons? It's really different to and is there any sort of thinking as to why it's so?
Well, if you look at the 4 Galilean moons, they're Ganymede, Callisto, and Europa, they're all made of water ice on the outside. It looks different because of cratering, but the surface, it's all water ice. They're all something rocky with something icy. So in that sense, they're very similar. Io looks a bit different at first sight because it doesn't have the icy layer, but that's just because it has lost it. It's so close to Jupiter that it gets very hot because of these gravity interactions that I mentioned, and as a consequence of that, it has lost all its ice already. So it started out being relatively similar. Something icy with something rocky.
So why is Ganymede the focus rather than Europa?
Because it's easier. The closer you get to Jupiter, the more damaging radiation you'll have, and Ganymede is just a lot easier to operate a spacecraft for a long period of time. Yeah.
So would it be possible to see Europa through like a good telescope? Like
See it with binoculars.
we'll put our telescope here, we can view Mars. So would it be possible?
Well, you can definitely see it with even binoculars, but
you'll be able to see. I was thinking that.
but considering that even with Hubble it's difficult to see any. I think with Hubble you can just about distinguish some of the surface features, so I don't expect that with equipment on Earth you'll be able to see much of Europa's surface, certainly not with. Yeah. Maybe people have tried, but most of what we know from Europa is coming from Hubble telescope, big equipment. I assume it's very difficult to get any information. Well, it's far enough to be able to distinguish them.
It's not a single telescope, but it's just here like a small dot.
Yeah.
I think some of Damien Beech's images of Jupiter do actually show the Galilean moons as small dust, but you can't see any real surface detail or anything like that. There's high resolution images.
Or the ELT, much better resolution.
Of the surface topography, is there a lot of difference between the pole and the equator?
Is there a specific reason that you're asking that, or?
Well, colder at the poles, and you get more movement at the equator.
Yeah.
Just looking at the pattern, is there anything significant?
Well, I don't know of any difference. I would say from these pictures it looks broadly the same everywhere. It seems kind of random, and that has to do with the fact that this whole ice shell, it's like a shell. It's not connected to, it's only connected to the liquid layer. So this ice is essentially floating on the whole moon, and it seems like it's actually moving with respect to the moon. So this ice layer is just wobbling around. So throughout Europa's history, different sides of the ice layer have been looking to different directions.
Sergey, did you have a question?
Yeah, it's more like common. New Zealand is far away from Europe, where JUICE is now in preparation, but I'm just back from overseas, and in the Netherlands, in Astron and JITE, we discussed our participation in JUICE in two ways. One way is with VLDI, very long design geometry, we can pinpoint location astronomically on JUICE when it flies in different positions. And the second one, we can receive the signal from JUICE. And looking at shift of the signal in terms of frequency, we can determine velocity and drift of this shift, acceleration, and drift of the drift, the next derivative. So we can come to that slide where we can judge about inner structure.
Yeah.
So we will be part of it. And from European radio telescopes, they can do it in one period of time. From Southern Hemisphere, we can do it a different period when they fly by. It's like what we did with Phobos when determined its mass and therefore density. Where observing Mars express flybys.
Yeah.
And just a comment and question: do you lecture? You should. You are very.
What should say an answer for a job?
Okay, there are no further questions. I'd like to thank Hans for a very enlightening talk and very clear talk. Thank you very much, Hans. One thing, if people haven't seen it, I think the astrophotography competition is still on display in the Matariki room.
It's your last chance to see it because it gets to seal tomorrow, I believe. And the influence of black telescope is not operating at the moment, it's still in pieces. Going for its upgrade. But if you dig outside and look back at the moon, you might see there's a very faint halo around the moon tonight. So that's pretty.
But before you go, Hans is actually in New Zealand for another reason. He's looking at a link between celestial navigation of spacecraft, like JUICE making its way to Jupiter, and Polynesian navigation, how they got to New Zealand using the stars. So did you want to just spend 5 minutes just very quickly? I mean, he's looking for help with this because obviously living in Belgium, he's not close to Polynesian resources, and that's one of the reasons he's here in New Zealand for his trip today.
Yeah, if you can a few more minutes. So I am interested to do some kind of project to compare spaceflight with JUICE with these waka journeys. So you're from New Zealand, you might know more about this than me. So people have built these traditional canoes to travel from New Zealand to Easter Island using navigation by the stars. And this made me realize that there are some similarities, sometimes on an abstract level, sometimes very practical level between space voyages and these ocean voyages. So I think it starts with a drive to explore. So I think both space explorers and ocean explorers have a certain drive to explore in common. And I think there is a bit more to be compared. So this drive to explore leads us to environments that are very suitable for human beings, like oceans and space. And this leads to certain problems and solutions that are sometimes similar between space and ocean voyages on an abstract level, but sometimes on a practical level. For example, well, to start moving, wakas use sails, and space wakas start to use sails now as well. So this is the first space sail, let's say. So here we have our spacecraft.
Akatsuki is called.
I think Icarus?
Oh, Icarus.
Yeah.
Yeah, they launched too.
Yeah.
Yeah.
So it's a Japanese thing. So it's a spacecraft and it's using a sail to use, well, the light of the sun to move through space. A problem that both share in common is the weather. So if you're traveling over the ocean, you need to be aware of storms and stuff like that. And in space we have storms too. We don't have the wind, but we have the gases from the sun that propagate to the solar system, and sometimes you have storms in this gas, and that could cause problems for people in spacecraft or spacecrafts themselves. And then last but not least, the ocean voyagers, they use the stars to navigate. This is still being done in space. This is Alexander Kurst, a German astronaut who's currently in the ISS. And this was during his training, he was trained to use stars to point the spacecraft in case the normal navigation systems would fail. But just about every spacecraft uses navigation by the stars. This is a star tracker. It's a camera that's pointed at the stars to figure out, based on the knowledge of the map of the stars, which direction the spacecraft is pointing at. So, in short, what I want to do is compare these waka ocean voyages and space travel to make people interested or involved in either one aware of each other from a unique perspective, essentially make a bridge between the topics. And I want to do that by starting a conversation between a space waka person and some ocean waka person to dig deeper into this topic. So, and I'm looking for people that have feedback on this topic, or some collaborator who would work with me.
I noticed on your slide at the bottom it said it had Dr. Matamua, he's at Waikato University, I think.
Yeah.
Have you talked to him?
I've been in touch with them. Yeah.
Right.
Did you watch the movie called Moana?
Yeah, okay, I'll watch the end then. Yeah, so, yeah, I'm sure you're already saturated with talks, slides by me, but if you have any feedback or suggestions on this idea, just let me know. Maybe after the talk. Thanks.
Thank you.